Hello everybody, and welcome to Theorem 5.1. We are looking at page 36 of the workbook here. And up to this point in this section, we've talked a lot about calculations involving permutations and some notation. And now we're ready to make some more general observations about permutations in symmetric groups. Okay, so in this video, we're going to be looking at theorems 5.1 and 5.2. Let's start with Theorem 5.1. This is about products of disjoint cycles. We're going to have to define what we mean by the term disjoint, which we'll do in a minute. Let's take a minute to read this theorem together. So it says that every permutation of a finite set can be written as a cycle or a product of disjoint cycles. There's that word disjoint again. Okay, and I think the easiest way to illustrate this is just with an example. Okay, so if we focus our attention on the permutation group S4. Okay, a permutation, we could describe a permutation in S4 as follows, just a specific example. Okay, the cycle 1, 2, 3 composed with the cycle 2, 3, 4. Okay, that represents a permutation in S4. Okay, now my first comment here is that this product of cycles that we wrote down is not disjoint. And the reason it's not disjoint is because it shares the number 2. Notice that 2 appears in both of those two cycles. And so what this theorem says is that there should be a way to rewrite this permutation so that it's either a single cycle or a product of disjoint cycles. In other words, cycles that don't share a common number like 2. Okay, and the nice thing is we can come up with this disjoint cycle representation by just doing the same calculation that we've done several times before. Just ask ourselves, if we compose these permutations, what do we get? All right, well, let's start with the number 1. Okay, notice that in the cycle to the right, 1 doesn't move, and then 1 goes to 2, so the net result is that 1 goes to 2. And let's see, where does 2 go? Well, 2 is going to go to 3, and then 3 wraps back to 1. So 2 is going to map back to 1, so our cycle closes. And 3 is a number that we haven't visited yet, so let's ask ourselves where 3 goes. 3 goes to 4, and then 4 doesn't change, so net result is 3 goes to 4, and then finally 4 maps back to 2. 2 goes to 3, so 4 is going to wrap around and hit 3. Okay, and notice that this representation that we came up with is disjoint. Those two cycles don't share any numbers. Okay, and that's what we mean when we use the word disjoint. So it's a product of disjoint cycles. Okay, and this theorem says that you can always do that. You can come up with a representation like this where you've either got a single cycle or a product of disjoint cycles. Okay, so we could do one more example here, and I'm going to leave it to you to confirm my calculation here, but if you take the permutation 1, 3, 4, compose it with the permutation 2, 5, 3, now we'd be doing a calculation maybe in S5. Those cycles are not disjoint because they share 3, but if you do this calculation, here's what you can confirm. Okay, you get a single cycle. Okay, and again, I'm going to leave it to you to just check and make sure that that calculation that I did is correct. The theorem just says that we can always do that. We're going to always be able to represent a permutation in one of these two ways, product of disjoint cycles or a single cycle. Okay, let's move down to Theorem 5.2. What does this say? Okay, so disjoint cycles commute. Let's read this together. So if the pair of cycles alpha equals A1 through AM and beta equals B1 through Bn have no entries in common, that means that they're disjoint again, then alpha beta is equal to beta alpha. Okay, now you might look at this and think this is kind of weird at first because we just made a big deal in a previous example about how symmetric groups are non-abelian if n is greater than or equal to 3, and this is telling us that you compose in either order, you get the same thing. But remember, the key word here is disjoint. It's not saying that we always have commutative composition just in the case where the cycles are disjoint. Okay, so to give you an example, theorem basically tells us that if you took the product of the cycle 1, 2, 5 with the cycle 3, 4, notice that those are disjoint. Okay, 1, 2, and 5, and 3, 4, they don't have any elements in common, and so because of the fact that they're disjoint, we could write it in the different order, in the other order, and they have to be equal. Okay, you might think about why that makes sense. Okay, I think if you ponder that a little bit, you might agree that it kind of makes sense that if the cycles are disjoint, we should be able to write them in the different order and get the same thing.